This call is now being recorded.
Hi, morning everyone.
Morning, sir.
Morning. I think we just start ya. Nabiha baru masuk. Morning.
Morning, sir.
Okay. Today we're going to look at magnetic field. No more echo, right?
Okay, previous week, I have sent you video on DC current and also AC current. I put it together because even though AC is the last chapter, some of you asked me whether the syllabus already finished. Not yet, actually. Still got 2 more sub-chapter. Today, we're going to look at one, and then next week, another one. Okay, and then we finish. Then we look at passive friction. All right. Okay, today's one is magnetism. Okay, today's one is actually chapter 6. If you look at this one, you can pin this one here, right? Okay, this one here, right? Okay, this is your syllabus for the chapter 6, magnetism. Today we're gonna look at this one, magnet and magnetic field, and then magnetic force, magnetic field due to current, magnetic torque, solenoid, and current. We skip Ampere's law. Ampere's law is too difficult for us to describe on my whiteboard. So I will use, I will record a video especially for Ampere's law. When I finish, I will upload the link to you. Okay. So we will skip 6.5 and then we finish 1.2, 3, 4, and 6. Okay. All right. So first one. Anyway, minggu ke berapa ni?
11,
11,
sir.
12?
12, sir.
Can't hear you.
This one, I think minggu 11, right?
Sir, sound, sir, double.
Huh?
Sound double.
Sound double ke?
What is wrong with that? Yeah?
Sir, buka dua-dua mic.
Think so. Have to switch on one.
So, I click on this one. How about now?
Okay, sir.
Okay. Okay. Good. Now, our first one is this magnetism. Now, you already learned electric field. Okay. So, your electric field is actually cannot exist without our magnetic field. So in the whole universe, if you see electric field, there will be magnetic field. They are always together. That's why you have electromagnetic wave or electromagnetic field. Well, but in certain cases in which the cases are very simple, you can actually have only electric field or magnetic field. But you have to make sure that two objects must in stationary condition. Okay, for example, a charged particle, stationary, they produce only electric field, no magnetic field around them. But once you started to move the charge, then they're going to produce magnetic field. So there are special conditions that we can actually have only that field alone. Magnetic field is a little bit more difficult to produce alone because they are generated from electric field. So once you detected magnetic field, then we must have somewhere around there electric field. Okay. Now we start with our magnetic field or magnetism. Okay. Can you see the writing? Can I? Okay, our first one is what is magnetic field? Okay. What is magnetic field? That is a question. Now, magnetic field can be divided into actually two types. Number one is the natural magnetic field. So I will use short form here. MF stands for magnetic field. Now, natural magnetic field, we know it is very familiar when you talk about compasses. Now, of course, you don't use compass when you're driving a car, right? Because you're using GPS system. So last time before GPS or satellite put on the sky, no handphone yet. So anytime you want to go and explore somewhere you're not familiar with in the ocean and so on, you are depending on compass because that one is the detector for magnetic field. So we look at our Earth. Okay, this is our Earth. Now our Earth rotates at the equator in this direction, and this one we call the axis of rotation. Okay, so this is the axis, and it takes 24 hours to make one complete rotation. Now, where is the North Pole? Up here, and this is the South Pole. But when we mention North Pole or South Pole, we have to be very particular. When you look at the map, this part here is called North Geographical Pole or North Geological Pole. And this one here is South Pole or South Geological Pole. When we mention, normally in normal conversation, when we say North Pole, South Pole, it refers to these two. Okay? But in our physics, we have another two poles actually which are a bit different from this one, or you might say totally opposite. Our north magnetic pole, okay, is somewhere here, not exactly on the south geological pole. It is somewhere here, offset a little bit. Now this one is our north magnetic pole. Surprise, right? Our north magnetic pole is actually at the south geological pole. And then directly opposite here, which is also offset a little bit, this red color one is our south magnetic pole. Okay, so that is our magnetic pole and also our geological pole. So don't get confused with that. Okay, now if we draw our magnetic field for this one, we're going to have magnetic field that looks like this. Magnetic field always start from north to the south. Okay, starting from here, go out, and then come back to the south pole. The direction is from here, yeah. And the other side also do the same thing. Okay, one coming up here, and then of course, the further you go, the bigger is the pattern. Okay, the bigger is the pattern. So also the same direction, like this, coming into the north pole. And the further one we normally cannot complete here because they are too large. The magnetic field of the Earth can actually extend about 2 to 3 radius of the Earth itself. Sometimes, because of solar storm, when the sun becomes active, they push out our Earth's magnetic field can be lopsided. If this one facing the sun, this one will be compressed, the other side will be extended to about 5 radius of the Earth. This one is only during solar storm, which is quite seldom we have, but once every few years, the sun will become a little bit angry or active, then that is what happens. All right. So remember, that is the pattern of our magnetic field of the Earth. And remember, the magnetic field is from the southern part of the geological world. And this is our north magnetic pole. And up at the north geological pole, that is where our south magnetic pole is located. Now, one more thing about our Earth's magnetic field is why our Earth's magnetic field is not exactly there and exactly here. because this one shifting all the time. Our magnetic field shift every 750,000 years. Okay, we call that one magnetic field reversal. Okay, magnetic field reversal. So that means every 750,000 years. Okay, our Earth's magnetic field at this moment is, this one is the south pole, this is the north magnetic pole. After that amount of years, it's going to flip again. So now, after that amount of year, we are going to have north magnetic pole exactly on the north geological pole, and the south magnetic pole is at the south pole. And that one happened for the past few hundreds of millions of years. Okay, so that one is such a natural process. Now, is there anything that can happen if during the magnetic reversal period? Yeah, it can actually affect the radiation from the sun, because when it rotates, certain part will be exposed to more to this solar radiation and also from outer space. But it won't kill us. If it kills us, we actually won't survive. Okay, but luckily it's not doing much damage. But instead of that, it actually helped our evolution, because when the sun, when the Earth's magnetic field rotated, there are some loophole, especially this area. They actually allow solar radiation to enter, do some changes to the DNA of the living things on the surface of the Earth every about 1 million years like that. So you see evolution happen. So it has been happening for so long already. Okay, so that is something that natural, and that one we cannot change them. We cannot change them. In our solar system, there are eight major planet and one dwarf planet, which is the Pluto. Altogether, we got 9. The one that you learn is 9. We actually have 16 planets, actually more than that. Now, Earth has a magnetic field that is average. Okay, Mars has very weak magnetic field. That's why they cannot actually protect the any living thing on the surface. Well, according to study from the space probe sent by this advanced country, they realized that before this, Mars actually have magnetic field. Why it got destroyed? That one have a lot of theory. You can also think of one next time. Now, Mercury definitely no magnetic field, because Mercury is too near to the sun. The magnetic field are actually superimposed by the Earth, by the sun magnetic field. You don't want to stay Mercury, too hot. Okay, too hot. Venus have very strong magnetic field. That suggests one thing: the core of the Venus is still in liquid form, like our Earth. All right, but their magnetic field are weaker than our Earth. Okay. Next, you come to Jupiter. Now, Jupiter is a gigantic star, a gigantic planet, and its magnetic field is about 10 times the strength of the Earth's magnetic field. So if you go there, you're exposed to that magnetic field, maybe your gene get mutated. Okay, your gene will get mutated, and that the possibility that for astronauts that passing through the area, if they're not protected by the shield, they will get some damage in their bodily cell. Okay, and then other than that, Jupiter, after that, Saturn, Uranus, and this Neptune, they all have very strong magnetic field because they are huge in size. Okay, so that is happening in natural. Now, other than that, we have man-made magnetic field. Then we have man-made magnetic field. So that is P, man-made magnetic field. Now, what do you mean by man-made magnetic field? Man-made magnetic field means we produce magnetic field so that we can use them. Okay, one of the most important discovery of the invention of the magnetic field is this. You have soft iron core, and then you put wire around, okay, and you supply with current. You are producing very strong magnetic field here, and also this side. It can be, this case, this is going to be north and this is south. Now, it looks very simple. We call this one electromagnet. Now, this electromagnet actually is used throughout our whole engineering and science and technology. Why? Because this is a basic for movement. motor design all based on this. So you have motor in your fan, motor in your aircon, motor in your hard drive, motor in a vibration device in your handphone, and so on. They can be from very tiny micro motor to gigantic motor used to move a floodgate and so on. Maybe whole building can move up and down. Okay, so this is what we have starting around in 17th century by Michael Faraday, or 18th century, like that. Okay, it's a very simple discovery. Of course, the first thing they use this one for is bell. The school bell based on this electromagnet. Well, this is man-made because it does not exist in nature. All right. Now, this is one of the most important ones. Man-made. There's actually a lot. I mentioned this one because we keep using it until now. Imagine there is no magnetic field. Maybe our civilization is going through in another direction. Okay, not the direction that we have like now. You have this electric drone and so on, right? So imagine that if we don't have electric field, electricity, maybe our civilization is going through somewhere even better, or maybe even worse. All right, so that's what we have. So sometimes we just have to trust our past of civilization and go ahead with the knowledge that we have. Maybe utilize the one that we have here. Okay, how do we utilize magnetic field from planets? Well, as I said just now, you use compass to navigate so that you don't get lost in the jungle or in the sea and Earth's surface. Now, if you go to outer space, you know Jupiter has 10 times stronger magnetic field than Earth, right? Now, you can actually string wire across attached to the spacecraft. You orbit the Jupiter, maybe just 5 rounds, your battery can be fully charged because any wire passed through magnetic field is going to produce electricity. That one is in chapter number 7. We're going to learn that in chapter number 7, like this also. All right. So that is application. If you have the knowledge, then you go to outer space. There is a lot of way that we can actually supply ourselves with energy, especially electricity. Okay, because our whole civilization is based on electricity. Okay, imagine you go back home, no electricity. Now all this Google Meet station is gone because no electricity, no internet, no nothing. All right. Okay, so that is our man-made, but we know that these natural magnetic field, we cannot control them, so we're not going to discuss much on this one. So we're going to further discuss man-made magnetic field. Okay, man-made magnetic field. So far, is the video clear now?
Clear, sir.
Clear, okay. If I look like a cartoon during the Google Meet, let me know, because last time my line is not good. Now should be okay already. Okay, now our next one, our magnetic field will be this. Okay, the symbol for magnetic field. Okay, magnetic field strength is symbol B. Okay, symbol B. Now, why symbol B? The reason is very simple. Symbol B, because the magnetic field is studied by this guy. Okay. Okay. So the BS law, not bullshit. This is also not pronounced as Biot-Savart law. It is pronounced as Biot-Savart. This one is a French. Okay, so you have Biot-Savart. Okay, Biot-Savart pronounced as Biot-Savart. The B does not exist in French, so they have Biot, okay, and Savart. Just like my T is not there. Okay, so Biot-Savart sound nice. So I could be studying actually in France rather than Malaysia. Okay, magnetic field strength is actually defined. Okay, we define magnetic field. Magnetic field strength, MFSB, is a magnetic field is defined to be, okay, the force, okay, per unit charge, per unit velocity, okay, per unit velocity. Now, from statement maybe not really clear, but if you write down in equation, it is like this. B magnetic field, the magnitude is equal to the force over the charge, okay, and then divide also by the velocity. Okay, so that is our magnetic field definition. Now we look at the unit for our magnetic field. The unit for magnetic field, we have two important ones, but we only adopt one on here, our SI unit. This one is Newton, okay, and then per coulomb, and then we have this meter per second -1, okay, -1. So now this is complicated, right? So this guy, VO so far, actually simplify become T, which stand for Tesla, okay, which stand for Tesla. So our unit for magnetic field in SI unit is Tesla, okay. Other unit, other non-SI unit is Gauss, okay, Gauss. You remember Gauss law? Gauss also not only successful in electric field, you have 4 Gauss law application, but it is also very important contribution in magnetic field. So we have Gauss, the unit is G, okay, unit is G. Now, what is the relationship between Gauss and G? Well, not very sure because I seldom use Gauss, but 1 Tesla is roughly 10 to the power 4 Gauss. Okay, about that, there are some number in front there about that. So when you mention Tesla, it's actually a gigantic unit. What is our Earth's magnetic field? Okay, for example, the magnetic field of the Earth's surface at equator, near to equator, near the surface, is equal to 5.5 10 to the power -5 Tesla only. Okay, -5 Tesla only. So it is about 55 or worse than that, smaller than that is 0.55 Gauss. Okay? 0.55 Gauss. So our Earth's magnetic field is very weak. But we can produce magnetic field using technology to produce like 2000 Tesla, okay, magnetic field. What is that magnetic field for? That magnetic field for the study of cryogenic process, process that you need superconducting and so on. Okay, so that one can only happen at very, very low temperature. Okay, so that is the example of the magnetic field that we have. Okay, so now we're going to look at the next one is after you study the magnetic field, actually where does this magnetic field formula come from? This magnetic field formula come from the definition for the force. Okay, so the second part now, we are looking at the second part is the magnetic force. Okay, magnetic force F. And normally we put a small b there. The b represents magnet. Okay, magnet. So magnetic force. Now we have to assume something like this. Let's assume that we have magnetic field pointing to our right hand side, or that one is a positive x direction. Okay, positive x direction. So we have this magnetic field. I give it a symbol B. It's a vector, so I put a vector sign there. So the blue color is the magnetic field. Now, let's assume we have a charged particle. Assume positive. Eh? We have a charged particle with a charge Q. And let's assume it moves in this direction and cut through the magnetic field with a velocity V. Okay, with a velocity V. And then another important thing is the angle where it cut through the magnetic field in that direction is this one, theta. Or here is also theta. Everywhere is theta. So we can only use the following formula, yeah? Only when the magnetic field are uniform. You see, they are all in the same line. The difference between the line and the same, they're all point in the same direction. If you have something like this, for example, magnetic field, okay, like that, this is not uniform. Okay, the charged particle that move here and the charged particle that move here is going to experience different effects. So this one we call dynamic magnetic field. You don't study dynamic magnetic field because this is too difficult for you. But if you take out physics, continue with physics next time. Then you're going to study those dynamic and static and all together. Okay. Now, this charged particle have a charge Q, velocity V, penetrate into the magnetic field. So in that case, the particle is going to experience magnetic force. Okay. First, we want to know in what direction is the magnetic force exerted on the charged particle. So you're going to use your right hand rule. Okay, right hand. Okay, right hand. So this hand here is damn important. Okay. Now the finger must be able to curl. Okay, like that. You can see my finger curling. Oh, so you know. Okay. The thumb is to point to the direction of the force. Okay. So this one, so that why we curve it, so that we want to curve it from V, from the V, the velocity, we want to curl it to the direction of V. Okay. Now I use this one as an example. Yeah. Before we calculate the magnitude, first we point at V. This one first, velocity first. Yeah. So thumb we don't care. Thumb we just extend only. So now we have here in the direction of the V. But you see, there are so many ways I can point to direction of velocity. You see, 360 degrees. I can point towards velocity. But there's only one position of my hand that my fingers can actually bend to magnetic field easily. Not like this. Like this, I had to bend using my brute force. Okay. So this one also cannot. I cannot bend easily naturally like that. It's not natural for my finger to bend down here. And also not like this. So the best is like this. You see or not? You can point to the velocity and then your finger, you can naturally, at your own will, point or bend your finger towards the B direction, you see? Okay. So that is your position. That is already correct. So again, I can point to velocity in any direction, but there's only one position of my hand that I can bend my finger towards B easily. Not like this, not easy, and not easy. Try to imagine if I have an angle of 180 degrees, you try to bend your finger 180 degrees, you might ask your parent to help you to break your finger. Okay, so this one can. See, until 180 also no problem. So where is our palm pointing? Our palm here is actually pointing into the whiteboard. So that means this charge is going to experience a magnetic force. We normally draw near to it. Direction that go into a surface, we normally use X or cross. Okay, and you label the force near to it, FP. So it means that this charged particle is going to experience a magnetic force into the whiteboard. So that means this area here is a magnetic field all pointing to your right hand side. Now there is a positive charged particle enter at a certain angle. Enter. What happens is it's going to experience a force. Pull it in. So instead of moving straight to the ceiling, it's going to move, curve in a circle. Still moving to that side. So it's going to curve in a circle and started to move in a spiral direction. Okay, in a spiral like a spring, like a helix. Okay, so that is what happened to this particle now. Okay, so there is a direction. Direction is determined using right hand rule. Okay, right hand rule. Now, next one is how big is a force? How big is that force? Our force FB is given by this formula. Q is a scalar quantity. So we multiply it by the velocity cross the magnetic field. You already learned this, right? Cross product. Okay, cross product. So what does cross product give you? So the magnitude of the force now is equal to Q. This one is going to be V sine theta, right? Cross product is sine theta. Dot product is cosine theta function. Okay, so if we take out the bracket, we have a magnitude of the magnetic force to be QBB sine theta. Okay, sine theta. That is our first formula for our magnetic force. If you are talking about one single charge particle, okay, one single charge, all right? Okay, next one. Next one, I'm going to extend that formula not only to one charge, but a lot of charge. Okay, a lot of charge. Meaning, how to get a lot of charge? So you use a wire, allow current to pass through. There will be a lot of charge inside there. So that one is magnetic force. Number one here is on a charge. Next one, on a wire that carry current. Okay, carry current. That is slightly different, but the formula actually are quite the same. So first, we draw our magnetic field again. Here. Okay. So this is the magnetic field B, and then we draw a rod inside. Okay, a rod. Current. Okay, current. This is a conductor. Okay, we call it EQ, and the length of the conductor is L. Okay, and we assume that the current flow inside the conductor is this direction, I, and the rod, or indirectly, the current is making an angle theta with a magnetic field. You know? Now, this current, we know it is what we call that, scalar, right? Okay. Now, how about L? Length. Length in this case is scalar. But what we want to do is we want to draw a displacement vector in the same direction here. So this is a displacement vector. So displacement vector supposed to have a vector sign. So this displacement vector is pointing from P to Q. Is the same as the length of the conductor, but it has a specific direction, point from P to Q. Okay. So now we have enough information. The displacement vector, the current, the angle, and the magnetic field. Now we want to find out the direction of the force. Okay. Again, we're using right hand rule. Okay. Now you see just now we have positive charge, right? And then our current is flowing in that direction. Now, what is current? Current is defined to be the rate of flow of positive charge. Okay. But now we know current is actually the electron move in the opposite direction. That one will be other time. That's some other time. But at the moment, we assume that current is the direction of the flow of positive charge per unit time. Okay. So we can assume now this is a direction of the velocity of the charge moving from P to Q. So again, you see, we're using the right hand rule again. So pointing from P to Q, there are so many positions, but there's only one. You can bend the rest of the finger to the direction of the magnetic field. You know? And the thumb still point in. So we have force. Okay? A force that moves inward or pull the conductor in. So we can still use the same symbol. That is the magnetic force. Normally we label for a conductor that's that long, we label the force at the center. Center of mass. Okay, center of mass. All right. So now that is the direction using right hand rule. Now we're going to find what is the formula to calculate this. The magnetic force now in this case is I L cross B. Okay? I L cross B. You see the format are exactly the same. Later I will show you. Actually, they are the same formula. Okay, they are cousins actually. Now, the magnitude of the force is equal to I L B sine theta. Well, from appearance, equation 1 and equation 2 are actually two different equations. But when we actually take out this one, okay, we can actually prove that this one is equal to that. Okay, this is what I'm going to show now. Let's say you see, from FB is equal to QB B sine theta. Okay, why I change this one into bracket? The reason is the velocity is actually equal to distance divided by time, right? Okay. Now, instead of divide L by T, now you divide Q by T. Okay, you divide Q by T, take out the L. Your Q divided by T, what do you get? This is current, right? Oh, what is it? Bottom left. Okay. So Q divided by T is current. So now you get I L B sine theta. So see the two equations, they are actually the same. It's the only difference shown in the physical characteristic only. Charge we cannot see, of course, but we can measure them. Conductor we can see. Okay, conductor we can see, but we still cannot see the current inside. Current is a phenomena that had been studied by scientists for hundreds of years, but we never see current before. But if you want to touch a conductor, go ahead with the 240 volt. Well, that is how you feel about current, right? Early morning shock. Okay, so that is our magnetic force. Okay, number one on a single charge, and then number two on a wire that carry conductors. Okay, so far any question? No.
No,
Any
sir.
question?
No, sir.
No. Nomia also no. Others?
So far, no questions.
No,
No, sir.
Okay. So a sip of coffee and then we continue on. Okay. Our next one is, just now you see this. This one is, you have magnetic field, you put a charge and you put a conductor in, and if the charge is moving, then it will have force. And if this conductor carry current, then it will have force. But let's say you put a charge inside there. The charge is not moving. So when the charge is not moving, stay there, the V0, everything here becomes zero. So your force is zero. So meaning that a stationary charge in magnetic field is not going to experience magnetic force. Okay. Same like this conductor. If this conductor is stationary and it does not carry current, the force on the conductor is also zero. Okay. So that is what happened. And that is what happened in magnetic field. So there are actually four reasons in which case the force can be zero. Number one, the charge is zero. No charge, you put in a neutral particle like atom, which is not ionized, or a neutron, which is not charged, you put it there, no matter how fast you move them, it's still zero force. So remember, magnetic field only apply to particle that is ionized, positive or negative ions, okay? And they must have velocity. No velocity, no matter how big is your charge, also not moving. And then magnetic field, of course, it must be there. There's no magnetic field. What are we talking about? Of course, no nothing, right? Okay. And then angle is important. You see or not? What makes time become zero? When theta is zero, right? So when theta is zero, meaning that your charged particle is moving parallel with the magnetic field. If your charged particle moving with the velocity but parallel with the magnetic field, when it moves parallel, it does not cut through the magnetic field, so the force is also zero. Okay, that one you have to remember. But other than that, if the charged particle move in an opposite direction but still parallel, like for example, charge initially move from left to the right, parallel to the magnetic field, and then it move in the opposite direction, still parallel, we call that one anti-parallel. Anti-parallel, okay, anti-parallel. Anti-parallel, the angle is 180. If you check your calculator, 180 again is equal to zero. So in that two conditions, your magnetic force is zero. If the theta is zero, another one is 180 degrees. So the same thing applied here. Okay. So if your theta is zero, you put a conductor parallel, current either flow to the right or to the left, conductor is going to experience zero force. And then if there's no magnetic field, of course nothing. If the length is zero, if you have a conductor of zero length, in other words, no conductor, right? No conductor, what do you want to study? Nothing, of course, so nothing. That one is quite unlogical, right? current. When current zero, no matter how long is the conductor you put inside, no matter how strong is the magnetic field, you also experience zero forces. Okay, so those are the conditions where you are going to get zero force. Okay, all right. So that's it for the magnetic force on charge and conductor. Now we look at a few examples. How are we going to calculate, okay, that magnitude and also the direction using this one, and also your right hand rule? Yeah? Right. Example one. Okay, our example one will not involve calculation, only involve using your right hand rules direction. Okay, A, we have magnetic field pointing downward here. B, and there is a charged particle moving to the right hand side. Positive charge move in this direction perpendicular the velocity v. Determine the direction of the force. Okay? Determine the direction of the force. Okay. B. Okay. B is special a bit. I'm going to draw magnetic field enter the whiteboard. So I use this symbol. This means magnetic field actually enter the whiteboard. So I put B in. B-I-N, B in. And then there's a particle moving from left to the right. Okay. Left to the right. Okay. So horizontal. Okay. Also find the direction of the force. Okay. Next, C. Okay. C. How to represent magnetic field pointing out? We use point, right? Point. So this is dot magnetic field pointing out from the surface. Okay. So I'll call this one B out. Okay. Magnetic field is out. And then there is a particle moving in this direction. A charged particle is positive, move in that direction. Let's say 45 degrees. Then let's say 45 degrees. Okay. And then D, we have magnetic field. Okay, like this, moving to pointing to the left hand side. And then we have two particles. Okay. We have electron, and then we have proton. Now they are moving like, okay. Electron move to the right with velocity v. Proton move to the left with velocity v. Same velocity. Okay. So now I give you 1, 2, 3, 4, 5 minutes to solve that problem. Give you 5 minutes, then we discuss. Okay, done. 5 minutes. See? The purple color one. 5 minutes. Gone already. Okay. We discussed that. Example 1A. We have velocity to the left. So we stand from this position. There are so many directions, right? But there's one direction. You can bend your finger like that. Down, right? Towards B. From velocity point to magnetic field. So now your thumb point out. So that means the charge is going to experience a force outward. Okay, outwards. Dot. Okay, that is A. B. Okay, B. Magnetic field into the whiteboard, and then your charge particle is positive, moving to your right hand side. Now it's moving to your right hand side. You point there, but you need to bend your finger inward, right? So you bend inward, your thumb point up. So that means this charge particle is going to experience an outward force, okay? And this is a force direction. Okay. This one, magnetic field out, okay, outward, and then your charge is at an angle 45 degrees. Let's say 45. So we follow the direction of the velocity up, then we go up. But you need to orientate, position your hand so that you need to bend your finger out easily because out from the surface, right? So what I have here is 45 degree. This one cannot, like this cannot, like this also cannot. So like that, I can bend my finger up. So now my thumb is 45 degree in that direction. So I just have to try it, 45 degree like this. That is the force. Remember one thing. The force must be always 90 degree to the velocity. Yeah, 90 degree. This one also 90 degree. The force velocity to the left. So in between them 90 degree. This one also 90 degree. Okay. Well, that one is the ABC. Now D. Can anyone give me what is the force on the electron first? Anyone want to try? Amira, want to try? Electron. Hello? Ada. Manina. Tarifa. Tarifa Miza. Force on the electron. Anyone? Remember this one is anti-parallel, right? What did I say when we have anti-parallel? Remember? Hello? Nomia? Ada? Okay. Wonder whether you're there or not. Sayang.
We're here, sir.
Malcolm. Malcolm, what is the force on the electron? Anti-parallel.
I don't know, sir.
Okay. Anyone who know? If the charge travel parallel or anti-parallel with the magnetic field?
Zero?
Yes, zero. Good. The answer is zero. Because you remember what I told you, if your theta is 0 or 180 degrees, right? Zero. So that means in these both cases, the forces on the electron is 0. And the force on the proton is also 0 because This one is considered anti-parallel, and this one is parallel. Anything anti-parallel and parallel force is 0. Okay, so remember that. Don't go and calculate and so on. Finally realize 0 using right hand. Okay, now next one. Next example. Now involve calculation. Yeah. Example 2. Okay, I'm going to have magnetic field. Right. A charged particle field of 5.50 microcoulomb. Remember the unit? And then it enters the magnetic field with a velocity of, let's say, 3.0010 to the power 6 meter per second at an angle theta of 60 degrees. Okay, 60.0 degree. And the magnetic field is B, which is equal to 250 millitesla. Okay, millitesla. So the question is, find the magnetic force on the charged tube. Okay, on the charged tube. All right. So again, I give you 5 minutes. Try this. Let's turn this on around. 5 minutes. Waiting. Must try, yeah? Oh, very cold. Raining here heavy. Okay, time's up. Okay. We can actually start with the magnetic force magnitude first. Our formula is, because it is single charge, so it is Q V cross B, or the magnitude is QVB sine theta. Okay, so now this one is going to give us this value 5.50 -6 because of micro, and then velocity is that one 3.00 10 to the power 6. And then now these two will be cancelling. 10 to the power 6, 10 to the power minus 6, cancel. And next one is magnetic field, 250 milli Tesla. Okay. And the angle is 60. So don't forget the sine function 60. Okay. So you get 5.5 times 3, cancel already. And then multiply by 250 -3 times sine function of 60. Okay, my answer is 3.57. Correct? 3.5 Newton. You got it right?
Yes, sir.
Okay, good. Is that all for our answer? You got one more thing, right? Direction. Okay, direction. Well, this case is easy because we already have that previous, the knot is saying exactly the same set. So we have positive charge. This is the direction of the velocity. So there's only one direction, can bend your finger naturally to B. So the thumb point in. So this charged particle is going to experience the force that much 3.57 Newton into the whiteboard. Okay. So normally this question will carry about 3 marks. Okay. Formula I give half a mark. The direction half a mark. And this one, what value you put in here is about 1 mark. Answer will be 1 mark. So about 3 marks. Okay. Okay. Next example concerning the conductor now. Okay. Example 3. Now I'm going to put the magnetic field pointing up. Okay. Magnetic field pointing up. Same value 250 milli Tesla. Now I have a conductor here. Okay. The conductor is inside the magnetic field. Yeah. This is Q. Okay. The length of PQ is 100 centimeter or 1 meter. One more thing here. This is 90 degrees. And the current flow from P to Q. That is your current. Okay. The current I is equal to 10.5 ampere. Okay, 10.5 ampere. And then the magnetic field area, the width of the magnetic field, I call W, is 80 centimeter. That's 80 centimeter. So, this one. So now is calculate. The question is calculate. Okay. The force on the conductor. Okay. Calculate the force on the conductor PQ. All right. 5 minutes again. Okay, 5 minutes up. So our example 3. Conductor length is 100 cm. Okay. Magnetic field 250 millitesla, current is 10.5. If you look at the formula used to calculate, F is equal to ILB sine theta, right? Now, what is this length? In previous drawing, I show you that the conductor, the whole conductor is inside the magnetic field, right? But you have to remember, yeah, this length is not all the time always the length of the conductor itself. It must be the length of the conductor that is inside the magnetic field. So in this case, see, the whole length is 100 cm, but the only part that is inside the magnetic field is only 80 cm. So you can only use this length only, okay? The other part here and here is not exposed to magnetic field, so they don't experience magnetic force, even though the current passing through, okay? So you have to use 80 rather than 100 centimeter, yeah? Okay, so now we have this current 10.5. The length is 80 cm, so 0.80 meter. Magnetic field 250 millitesla and sine 90 degrees. So this one is going to be 1. Okay, so we calculate that 10.5 times 0.8 times 250 negative 3. Answer 2.1. Okay, I got 2.10. All right. 2.10, yeah?
Yes.
Whoever use 100, Tarifa, correct not?
Yes.
Okay. If anyone use the 100 centimeter, you get the wrong answer already. Your force will be larger than this one. So be careful with this. Not always come out like that in the exam, but there are possibilities because you need to know the formula. The L is the length of the conductor that is exposed to the magnetic field. Only this part here. Okay. The one not exposed, no matter how long they are not counted. Okay. Only this one. That's why I give you this one and also this to confuse you. Okay. All right. Next, one more thing is the direction of the force, right hand rule. So current to your right hand side, and then magnetic field up, right? So you have to turn your palm around so you can go up. So the thumb point outside. So the force on the rod or the conductor is out, and that is the magnetic field, magnetic force direction upward with 2.10 Newton. Okay. All right, so that is the example that we have. Of course, the tutorial example will be much more difficult than this. Well, did you watch the solution for the tutorial or not? I susah make the tutorial for you, so you better watch it. Okay. Anything don't understand inside, you can WhatsApp me again. So if there's any calculation mistake inside, I actually always make mistake inside there when punch calculator in. You know, sometimes I wear glasses, sometimes I don't wear, so I can hardly see my own punching actually. Okay, next one is magnetic field due to current. Okay, magnetic field due to current. Okay, there are 5 applications. You have straight conductor, you have arc, and then you have circular loop, and then you have solenoid, and the last one is a toroid. If you look at this one here, okay, you have a last one is the what we call it, the solenoid and toroid, and we're going to combine 6.3 and 6.6. Yeah, 6.3 and 6.6. Okay, this one done. Okay, next one. That is 6.3. 6.3 is magnetic field due to current. Okay? Magnetic field due to current, meaning that if you have a conductor, a current passing through the conductor, and that conductor is going to produce magnetic field around it. Okay, so there are 5 applications, 5 situations. We look at situation number 1. Situation number 1, that one is straight conductor. Okay, straight conductor that carry current. It must have current. No current, no torque. Okay. Now let's assume that we have this conductor carry current upward. Okay, in this direction. This current is I. Okay. Now let's assume again we are at a distance R away. This is the distance here. This is your distance R. Now the formula will allow us to calculate how strong is the magnetic field at this point. But before that, I want to recall what you learned in Form 5. If you have a current carry conductor, you know that there is a magnetic field around, right? And this magnetic field is something that looks like this. Remember? The further it goes, the more separated they are. And the direction of the magnetic field, you're using your right hand rule again. The thumb point to the direction of the current. So it seems like you're holding this one, point up. The magnetic field spin in that direction. Here, they all go in. Here, they all come out. So you have in, this one out. Okay. But last time in Form 5, you only learn the shape of the magnetic field. But here, now in your diploma, you're going to learn not only the shape, but how to calculate how strong is a magnetic field at a certain distance and in what direction. Okay, and in what direction. Yeah? Okay, so now what is the formula then? The formula here, let's say at this point, the magnetic field at point X. Okay, so at X, the magnetic field is given by this formula, mu naught times I over 2 pi r. So that is our formula for the magnetic field here. In physics 150, we don't have to derive this formula. If you want to derive, that one is going to take another 2 hours of video. Okay, so we don't derive this formula. And exam, they actually don't ask you to derive anyway. Not exam. You don't have final exam, you only have test 2 later. Okay, now this is a formula. Now look at what is mu naught. Mu naught is a constant, always related to magnetic field in vacuum. And its value is 4 pi times 10 to the power -7. This one is unit of Henry per meter. Okay, Henry per meter. And this guy is called permeability of vacuum. Okay, permeability of vacuum. It means that for every meter of vacuum, how many Henry of this energy per unit magnetic field can squeeze through into the vacuum. So it's not something that can easily understand. If you want to check more on this is not in your syllabus. You can Google them, and find the mu naught permeability of vacuum. There will be like 100 pages of the theory on this thing. Okay, this guy here is actually related to another one you already learned in our chapter 1, epsilon naught. Remember that? This one is the one that controls electric field. This is the one that controls the magnetic field. Okay, so now that is our formula, but we want to know what is the direction. What is the direction of the magnetic field here? So you want to know the direction, we have to look at the diagram from other perspective. So now we know current flow up. So now we're going to see the whole thing from the top. Okay. So from whole thing from the top, you're going to see conductor carry current a dot at your eyes level, okay, at your eyes, and we have magnetic field in a circular shape. Okay, and then the further it goes, the larger it goes. Okay, now how to determine the direction? Again, right hand rule. The thumb point out to the direction of the current, so all your magnetic field turn anti-clockwise. So in this case, it will be like this. So here will be to the left, here to be right. Now, our X position is on the left, right hand side of the conductor, so it should be here. Let's say it's somewhere here. Okay, so this is our X position. So you imagine that this circle is because of the vector of magnetic field spinning at the speed of light. That's why you see circular. Okay, you see circle. So let's say by the time the vector of magnetic field reach here, you snapshot. Remember your handphone got something called snapshot? So by the time you reach here, you snapshot. So what you see is this vector. That is your magnetic field vector at point X. But of course, that direction is because we see the whole thing from the top. Now, we know that if it is here, the magnetic field vector should be pointing away from us, right? So this is how you imagine it. This is the magnetic field. Okay, this is the conductor carry current up. Now the magnetic field is in. So now if I move it around like this, what you see now is this magnetic, the current pointing up, the magnetic field is up now. So if I turn back, you see things like this. So this chapter, you need a little bit of imagination, three-dimensional reality. All right. So it's not really that easy, but it's not entirely that difficult also. Okay, you just need to have some time with it, play around with two pen and so on and so on. Okay, so that is our magnitude and also this one. So you see, it depends on current. The larger the current, the stronger the magnetic field, and then the further you are from the conductor, the smaller is the magnetic field. Okay, all right. So that is our first one. Second one. Second one is arc. Arc. Okay. So what is arc? Arc is actually part of a circle. Okay, part of a circle. Okay, let's say I use this one for the part of the circle. Okay, center. Center. Okay, we have arc. This is the arc. This big arc is called the radius of arc. Radius of arc. Then let's assume this is our conductor. Okay. Right. Conductor we normally draw the conductor carry current, okay, in this direction. Okay, this is the current. Now the current is flowing in a circular path. And of course, this is what we call the center of arc or center of arc. And then there is an angle created between two radius of arc. So the theta is called the angle of arc. Okay. Now angle of arc must be in the unit of radian. Okay, it must be in the unit of radian. Okay. Now, what is the formula? The formula that you're going to use here is only to calculate the magnetic field at the center O. Not here, not here, not everywhere else. Only at the center. Yeah. Like this one, you can calculate anywhere, but not this one. So the arc one is actually very limited. You want to calculate here, you need a lot of integration involved. Okay. So now we're going to look at O. Okay. At O, the formula to calculate, okay, our magnetic field strength is this one. Mu naught multiplied by I, okay? And we know that the larger the I, the stronger is the magnetic field. So you see the first two parts is always the same. Mu naught I is always there. And then you need to have theta. Then you need to have theta and then divide by 4R. Okay, divide by 4R. I believe there is a formula if I'm not mistaken. Okay, so mu naught I theta over 4R. Yeah, that's the formula. Compared to this one is slightly different, right? So don't get confused. Yeah? Normally, students, if they forget the formula, when they look at the circular shape, then they always assume there is a pi there, but this one is the opposite. The conductor, okay, and then this is flat, so you got 2 pi. This one circle, you got no pi, right? That is a formula that we have. And then, what is the direction of the magnetic field? Same thing like this one, you use right hand rule. That one we also use right hand rule. See or not? Now, our right hand rule have to be changed a little bit. Then we change a little bit the right hand rule. So now instead of this one is the direction of the magnetic field, and sorry, just now this one is the direction of magnetic field. This one is the direction of velocity, right? Now I'm going to change. Now you have to use your fingers for the direction of the current and the thumb the direction of the magnetic field. Now, okay. So now this is what we have here. Our current, we follow the direction of the velocity. Now it curve, right? So you curve according to that direction. There's only one way to do it, either clockwise or anti-clockwise. So for clockwise, where is your thumb pointing? Inward. So that means your magnetic field here is actually point into the whiteboard or the paper. Okay. So remember, you use your right hand rule. The finger show in the direction of current now, and then thumb point inward. Okay, the thumb point inward. All right. So that is our arc. Okay, our arc. That one is the second one. Okay. Now we look at the third one. The third one is a full circle. I need something to draw full circle. Okay. Right. Right. Our full circle now. Cannot. Never mind. After 3 circular conductor. So we have circular conductor. Okay, now we have a circular conductor. Carry current, let's say this is the center, and the radius R, big R, okay, big R, center O. So this is the radius of the circular conductor, center of the circular conductor. And let's assume the current again Okay, now I want it to flow anti-clockwise. Current flow like that, anti-clockwise. Yeah? So first we want to determine what's the direction of the current, direction of the magnetic field. The direction of the magnetic field again is our right hand rule, right? Our right hand rule. So just now that one we follow like this, right? So now since this one is anti-clockwise, so we just follow anti-clockwise. So the thumb point out. So now we know the magnetic field here is out. Okay, it's out. Now, what's the formula? It's related to that one. Okay, it's related to that one. So our formula, remember, the angle theta, what is the value of one whole circle for the value of theta in radian? Anyone? One circle, complete circle, what is the angle in theta? Hello?
360.
That is in degree, right? How about in radian? How many pi?
2 pi.
2 pi, yes. 2 pi radian. Huh? So we have 2 pi radian. So now we know that here the theta is 2 pi radian. So what is the formula? You just need to put this theta into the original equation. So I get this. V is equal to mu naught I 2 pi over 4r. So finally our formula becomes cancel. We got oh sorry, where's my pi just now? Sorry, there's a pi here. My mistake. This one should be 4 pi r. I forgot about the pi. Okay, now your pi, you cancel the 2 pi and the 4 pi, you're leaving with 2. So you have mu naught I over 2r. Okay, over 2r. That is the correct formula. So this is our formula number 2. This is 1, this is 2, and number. Got it? So we always have this one related. But this one is a special case where your theta is equal to 2 pi radian, and this one is depend on how big is the angle. Okay. These are the 3 simple one. Okay, simple one. Okay, next one is our solenoid and also our what you call it? Donut shape. Donut shape has a name. Donut shape is called toroid. Okay, toroid in our mathematical term. Okay. All right. This one done. Our next one. Okay. Our next shape, number 4. Okay. Number 4. This one is solenoid. Okay. Now our solenoid is not any other solenoid. It must be a perfect solenoid. So we assume something like this. Okay. You have wire going up and down like that. Okay. But you see our solenoid here, there's a gap here, right? This type of solenoid, we cannot use our formula to calculate because when a gap is used, there is a magnetic flux instability inside. They are not uniform. We want it to be very close to each other. So when we say very close, they are touching each other. Okay? They are touching each other. So we will assume that our solenoid will be something that is like this. Okay? Okay. So I'll just draw the first one. And continue on, one after another. So there will be a lot of number of turns, right? So you can draw whatever you want as long as all the coils are touching each other like neighbors. Okay, now we have the wire come out from behind here. Okay, so now that is what we have. Very close, and we need other information. The length of the solenoid. Okay, this is the length of the solenoid. We call this one L. And then one more thing is number of turns. Big N. Okay, number of turns, big N. And then we need current. Okay, current that flow in and out. This one is current I. Okay, current I. All right. So now there is enough information. Our formula will only allow us to calculate the magnetic field at the center of the solenoid and also at the end of the solenoid here. Two locations. Okay, two locations. So this line, the dotted red line, we call this one axis of solenoid. Okay, axis of solenoid. And there are two locations that you can calculate. Center and end. There are two end here, left end and right end. And both of them have the same value. Okay, same value, right? Okay, our formula for the center, C. Our magnetic field at the center C, we normally put BC, is equal to mu naught multiplied by N over L multiplied by current I. Okay, by current I. But sometimes question can give you the value of N over L. Like this. Okay. So the BC can be like that also, where your small n is equal to N over L. Okay. It's the same. Okay, it's the same. Except the formula looks more compact, smaller. Okay. So that one is at the center of the solenoid, but we seldom use the center, right? We cannot reach the center unless you do research. For N of solenoid E, so the magnetic field at E is very easy. It's only half of the one at center. So if it is half, then we got two formula already. Half mu naught N over L times I, or is equal to half mu naught N I. Okay, so that is our formula for solenoid. Okay, but of course we also need to know the direction of the magnetic field. Well, that is easy, but we need another diagram to determine that. Let's assume instead of drawing the solenoid so near together, we're going to separate them so that you see how the current flow. Let's say I have this. Yeah. Okay, my current flow in here and out here. So from the front of the solenoid, we can see that the current all going up, because up, down, the other side, up again, right? So using our right hand rule again, but this time, we'll use this one first. Okay, determine the direction of the current first in front of the solenoid. Yeah? So you put your finger in the same direction of the current. Now see, so when they are the same direction, then the thumb point where the magnetic field come out. The place where the magnetic field come out is a north pole. Okay? This is where the magnetic field will come out. So this one is the north pole. Magnetic field only got two poles, north and south. So the one that comes in will be south. Okay? This one is the south pole, right? So now if I inverse the magnetic the current, instead of up, so now it's down, right? So down is this side is going to be north and that one is going to be south. So that is how we determine the direction of the magnetic field. Okay, magnetic field. So that is one way, the easiest one to determine the direction of the magnetic field in solenoid. Okay. Now come to the last one. Number 5 is called toroid. This one is donut shape. Okay, donut. Now imagine donut, right? Okay, but this one if we cut, you see circular shape, isn't it? That is our donut. Exactly donut shape like that. Okay? That is a donut shape. So our donut shape, we're going to draw. We see the whole thing from the top. Okay. Now we're going to put wires around them. Okay. The wire will be supposed to be very close, but if I draw very close, it's difficult to see. So I'm going to draw like this. Okay. But you must know that they are supposed to be very close to each other. Okay, now this is the wire going around a donut or tornado shape, and assume current in this direction in here. So now the current are all in this direction. Okay, it is in a different out. Current is high, and then we want the average radius. Okay, the average radius is from the center of the donut to the center of the thickness here. This one is called R. Okay, for R. And what else we have? We need current, we need R. That's it. Okay, that's it. So now, how do we get the formula for the magnetic field inside the donut? The magnetic field is in a circular shape, okay? But not everywhere are the same. Not everywhere are the same, but they are parallel to each other, no doubt. Okay. Now, our formula will be this. At that distance here, because you are from the center R, right? This is the center O. This is the center of the donut. Okay, center of the donut. So this place here, the magnetic field is given by this formula. We normally use mu. Okay, we have this what we call it, mu. Mu. This one. Okay, this formula here. We put it as mu not n I over length. Okay, it's the same formula as the solenoid, except now, can you imagine that your solenoid, you bend a solenoid, it becomes a toroid, a donut. Okay, you bend a solenoid, it becomes a donut. So what happens to the length? The length of the donut is actually equal to the length of your solenoid, L here. But for donut, we want to calculate the length of the donut is equal to the perimeter. Okay, so that L mu naught n I, the length of the solenoid here, the donut here is equal to perimeter 2 pi r. See that formula now? It's actually the same like that, except our L is not linear, but we are in a circular shape. So that one is L. Okay? That is an L now. So using R, you get 2 pi r as the length of the solenoid R. That is the formula for our toroidal shape. Okay, toroidal shape. Now, in what direction is a magnetic field spin inside? Well, look at the direction of the current. Current flow like that in front of you, right? So they are going clockwise. So the magnetic field inside here, all in this direction. Okay, because the current are like that. So that one is easy actually to determine. Okay? Got it? Now, can we take 15 or not? Because you got still one part, magnetic torque. You come back here again at 12:15. Is that okay? Come back at 12:15, yeah? I will leave this one on and maybe I'll let you hear some music.
Okay,
See you
sir.
again, 12:15, yeah? Oh yeah, welcome back. Can I start? Okay, our last part for this chapter 6 is a magnetic torque. Okay, magnetic torque. So what is magnetic torque actually? Magnetic torque is when you have a coil, you put the whole coil inside the magnetic field and you supply current and the whole coil will turn. Okay, it will rotate. Okay, it will rotate. That is because of magnetic torque. Yeah. Okay, this magnetic torque is 6.4. The symbol for magnetic torque is this symbol. Okay, we pronounce this one as tau. Okay, tau. Okay, let's assume we have a coil, rectangular coil. Right, rectangular coil placed inside a magnetic field. Okay, so this is the magnetic field. The whole coil must be inside the magnetic field. Yeah. Okay. So magnetic field B. And then this coil here, let's say it has a width here, A, and the length here of B. So we know that the surface area of the coil here is A times B. Okay. So the area of coil, this rectangular coil, A is equal to small a times small b, AB. Correct? So that is one. And then one more thing is we want the rotating axis to be here. Okay? We want it to be able to rotate in one of these directions, either turn like that or turning the other way around. So we call this one the axis of rotation of the coil. Okay, so this one is a rectangular coil. Okay, rectangular coil. Okay, next we need to look at the coil at a certain perspective. Okay, now we have this magnetic field, same magnetic field. So we want the coil to be at a certain position, already rotated at a certain position. Let's say this is the position of the coil. You know? Okay, so this is our axis of rotation. So the coil is already making a certain angle, certain angle, but this one is a bit complicated to see, but we can still label it. This one is A, this one is B, and the axis already making an angle compared to this one. So this is the same magnetic field we're talking about. Now we want to look at the whole thing from the top. Okay, the magnetic field still point to the right hand side. This is the side view. Ours here is a top view. the top view, we have this then magnetic field. Because magnetic field no change. So now imagine you see the whole thing from the top, yeah? But once you see from the top, your coil already rotated something about like that. Okay? And this is the axis of rotation, right? Axis of rotation. Now, why it rotate like that? Why it rotate like that? Because of the magnetic force, right? Now, which part of the conductor that is actually cut through magnetic field? This side here. You see? This side and this side. When it is rotating, this side A and this side A here is still parallel. The current flow parallel or anti-parallel to the magnetic field. So the A part, the shorter part of the coil, actually does not experience any magnetic force. The only the experience is the B side. Okay, so we don't have to worry about the A side here, but we need to draw it just to show that it is conductor. Now, the B side here, we will draw something like this. And this is the conductor side. And here, when you see it now, the conductor is here. This side here should be have the same size. The conductor should be the same size, but we ignore that one. Now, let's assume we have current flowing in the conductor like this. Let's assume current flow up here, go through here and down, and then go in a circle like that. So this is the current I. So since this part here is here, so we have current up and the other side down. So the one up will point at you. Okay, current point at you, and this one going down, current is going away from you. Now using our right hand rule, okay, our right hand rules, and what you learn also in Form 5 is this one, what we call is Fleming left hand rule, right? Fleming left hand rule is easier than this one because it applies all to 90-degree one. So FBI. So the thumb is the force, the index finger is the direction of the magnetic field, and this one is the direction of the current. So you use that one, which is easier. Now in this case, okay, you see the current is pointing out. Okay, so you have out. Okay, out here. Magnetic field point to your right hand side. Okay, point to your right hand side. So you have force going upward. Okay, there is a force going up. This is the force. So oppositely, this one is current in, magnetic field to the other side, so it's downward. Okay, downward. But you already fixed this one to be the rotating center, right? The axis of rotation. So what happened is this whole coil is going to rotate. Okay. In this case, is clockwise. So that means in this case, it's going to rotate like this. Okay. If I have something, yeah. If this is a coil, it's going to rotate like that. Okay, like that, because the coil is supposed to be like that. It rotates like that. So when I transform into this position, it's going to rotate this way. Okay. So now, what else? We also have some other information from the center of rotation here. This is the center of rotation O. Okay, O. So this distance from O is half A. Okay, because the total length is A. So here is also half A. When you apply a force onto something, and that something is at a distance away. For example, this one apply a force here, and it is at a distance from the center of rotation. So you're going to produce torque. Okay, you're going to produce torque. So now we're going to draw that the requirement to calculate torque. Now we are going to draw how far is the displacement of this one from here. So the displacement is half A. So we're going to draw this vector half A here instead of here. So now we have this half A vector. Don't worry about why it changed vector, but just follow that procedure. So how long is that? You just draw another vector, and then here the same thing. You always draw the vector from the center. This one is also a half A vector. Okay, half A vector, and you need something else. That something else is the angle. That is the angle. So let's assume we have an angle starting from the plane. Okay? We draw a 90-degree line, okay, passing through the center of rotation. That must be 90 degrees. And that dotted line is actually something you already learned last time. It is called the normal line. Okay? It is called the normal line, right? So our normal line is perpendicular to the plane of the coil. So now what does this normal line have to do? Your normal line is always perpendicular to the plane, so that means it's also always perpendicular to the half A here and half A here also, right? So now we need to find a way to determine the direction. Now remember, just now this thing is flat like this. Okay? It's flat like this. So now it started to rotate. Okay? It started to rotate. So we assume there is an angle in between them. So the angle normally is attached with this one to the magnetic field. Okay. So that one will be magnetic field here. So it should be here, right? This is the angle. So this angle I will call alpha. Okay, I will call this one alpha. And where is the alpha again for other part of the diagram? This one also alpha, right? Here. Okay. Here also. Okay. This one is perpendicular to this one. So when this one is alpha, so that means this one is also alpha. Right? So that means here is alpha. Okay? This one is also alpha. You know this again. This one also alpha. So I put this one orange color. This one also alpha. And then the other diagram, this one also. This one also alpha. So if this one is alpha, this one will be 180 minus alpha, right? This one is also 180 minus alpha. Okay. Now, in your term one, you already learned formula for torque. Okay. The same torque like this. Now, we're going to talk about torque. The formula for your torque is equal to R cross F. R is this vector. Okay. The force F is this vector. And the cross product produce something like this. The magnitude RF sine theta. And your theta is the angle between the R and the F vector. So you have R vector, F vector, the angle between them is 180 minus alpha. Okay. So we look at our formula. Now we calculate the torque on this side. So we call conductor 1, conductor 2. Okay, conductor 1 and 2. So what is the torque? What is the torque here? The torque for conductor 1 is RF sine theta, and the R is half A. Okay, half A. So we have half A. The force is F. We don't know the force yet. Now the angle we know is 180 minus alpha. So when we find 180 minus alpha, what is that value? So sine 180 minus alpha is equal to sine 180 cosine alpha, and then minus cosine 180 sine alpha, right? Okay, see what do we get here? What is this? This one is 0, right? 180 is 0. So 0 minus cosine 180 is negative 1. So negative 1 sine alpha. And it finally equal to sine alpha. No changes. No changes. It's still sine alpha. So our value here, T1 is equal to half AF sine alpha. Okay, sine alpha. But our torque number 2 is symmetrical. It's the same magnitude. Torque number 2, because everything are the same, half A and the angle also the same, the F is also here, only in the opposite direction. So now our torque number 2 is equal to half AF sine alpha also. Okay, no changes. So our total torque, this one is torque 1 plus torque 2 is equal to 2 of this one, 2 times half AF sine alpha. So finally we get AF sine alpha. That is our total torque. Okay, total torque. But we have a problem. We want our torque not in F. So now we need to find what is the force on this part of the conductor. The conductor have a length which is inside a magnetic field B, and it has a current I. Okay, current I. Now remember previously, when you put a conductor with current inside a magnetic field, it's going to experience a magnetic force. And that formula for the force is F is equal to ILB sine angle theta. Now, you look at this direction of conductor. The conductor is vertical. Your magnetic field is horizontal. So they are making an angle of 90 degrees. So your sine is going to be 90 in this case. Okay. So our length, what is the length L? The length L is B. So we have now IB. That one is the force here. Okay. That is the force here and here. So now we put this equation into here. We're going to get another equation. Torque is equal to A, and this one is IB sine alpha. Now, what is small a times small b? Small a times small b is the area of the coil, right? This one, area of the coil. So our torque now is equal to IAB sine alpha. Okay, sine alpha. Now, we're going to go further. You look at our coil, there's only one turn, right? One turn. So, for n turn of coil, okay, for n turns of the rectangular coil, our total torque now is equal to everything here multiplied by n. So we have NIA B sine alpha. NIA B sine alpha, right? So it's so easy to remember this one because the formula can be the position of the letter can be changed. You can actually change it to sine alpha, or you can change to Nabi sine alpha, or you can change to Bani sine alpha. Okay, so there are so many ways to remember them. There's so many ways to remember them. Okay, so you just remember either one of them. All right, so it is NIAB sine alpha. All right, so there is a formula for our torque. Okay, formula for our torque. This is called magnetic torque. Okay, magnetic torque. Right, magnetic torque. Yeah. Okay, so that's it for our this chapter. Except the Ampere's law, I will make a video on it. Then I give you the link. Yeah. Because Ampere law is a bit difficult to draw on the whiteboard, so I prefer to use a small A4 paper size. Okay, so record that one and let you know. And then I'll give you this tutorial number 6, and then try to do it, and then I will give you the solution in the YouTube also. Okay, so I'll see you again next week, and don't forget to do your last lab 4. Okay, that's it for today. Okay, I see you again next week. Okay, bye bye.
Thank you, sir.
Bye.
Thank you, sir.
Bye bye.
you.